Well, we would now then come to the, sort of a general discussion. So may I ask you, Roy, to switch back? Thanks again for your presentation. And
Sure.
may I ask all these speakers at least to turn their video on again, so that we have sort of a virtual panel discussion. So are there any general questions from the audience? Take-home messages? Are you worried about diffusion? Are you excited about diffusion?
So I guess I've got a question to kick things off. What at the moment is the single thing that's holding us back? Is it better analytical measurements? Is it better understanding of the parameters we're talking about and how they operate in natural systems? What hurdle do we need to get over in order to make big leaps here?
Do you want to take, or do you want to have a take on that?
Me personally? No, I'm asking you guys, the speakers.
I personally think it's manpower, right? So when I consider what happened in bicrystal diffusion experiments, it's certainly manpower that holds us back considerably.
I think it's a combination of manpower and, as Schumid pointed out, I don't think that we fully understand the concept of diffusion in its details. So there are systems where if you look at different experiments producing different diffusion data, diffusion rates, you can have an Arrhenius plot where you have for the same element completely different experiments. And it's really getting down to the nitty-gritty part on why do our experiments produce different data. So it's not that we had one case, for example, for the iron magnesium diffusion. We used the same experimental setup, we used the same analytical technique, and yet our diffusion data didn't show any dependence on the oxygen fugacity, whereas those from colleagues did. And it took a real long time until we started to understand why this is the case. And it basically came down to the aluminum content. Okay, so these are the things where you really need diffusion works, but sometimes we are missing points, and it's basically filling these gaps, right? And there's a lot of diffusion data that still waits for to be determined, right? All the anisotropy and so on and so forth.
Yeah.
So that's my take. Schumid, what do you think?
I could say, but Roy wanted to say something, and maybe then I could something.
Thank you. I was just going to make a point about the embedding chemistry behind what's actually happening. And one of the things that occurred to me in your talk, Thomas, is diffusion is one of the processes. I mean, and it's clear, you can see it exactly the same way that someone could mute themselves, maybe just some noise coming somewhere. But there's an embedding chemistry that's involved here. And one of the things I find fascinating about this, grain boundary diffusion, and then the movement of one chemical component from one phase into another phase, there is a chemical transition state involved there. And so looking at it at the sort of the atomic scale, as well as what I've just done is back up and look at the chemical reactivity at a much, much bigger scale, it seems to me that there's an embedding chemistry that goes along with the diffusion process that is fascinating and actually opens up our understanding of the actual mass transfer process. Does that make sense?
Yeah, it does. Yeah, I mean, I find that actually I feel myself like a kid in a candy store right now. So instead of holding back, when I see now the analytical possibilities that are there, the fact that, used to be that you had to set up specialized programs and things, and now everybody. Yesterday, I was at a short course where people were doing calculations on their tablets, so not even a computer. They're doing things on a cell phone, and so it's really coming down to manpower or doing things, because just in the last few years we've been learning so much more. Now, the one thing about all of this is that because we can now map trace elements and see how they're distributed, and because they determine significantly the diffusive behavior of materials, like Tommy pointed out, you're looking at iron, magnesium, and clinopyroxene, and you're not necessarily thinking of aluminum, and yet that turns out to be important. And so what I keep saying is what I call trace element crystallography will be a big component. Now we can measure where a lot of the trace elements, we can map them, but it'd be good to know where they're sitting. And that's where, synchrotrons bringing in a lot of possibilities. But that I think, knowing where these trace elements sit, and then of course, theory to work out how they're affecting diffusion, which again, we have focus, but because we can do so much more with computers and things now, there's a lot that can be done now that even 5 years ago, it was just not possible.
So we have 2 questions in the chat. Let's start with the first one. Talking about the Dodson's closure temperature and grain boundaries. How likely are grain boundaries to efficiently remove radiogenic isotopes to make an assumption about an infinite reservoir valid? I'm tempted to give this question to Claire, actually.
The data that we have from natural rocks, certainly looking at argon, for example, suggests that that is not a valid assumption. And we need to be very, very careful. The difficulty is how to measure it, because it's what we see now in the rock is an integration of all of the processes that have happened to that rock over time. And yet what we're trying to measure is one specific point in time. So I think you've got to be very, very, very careful. And you've got to combine all of the things that Katerina was talking about, that Roy was talking about, that Thomas was talking about, and also that Shumit was talking about this afternoon to try to unravel that infinite reservoir question. But personally, for a lot of thermochronology applications, I don't see much evidence from the type of data that I've collected that is a valid assumption. That doesn't necessarily mean I'm right. It's just I don't think we can measure it yet. Very willing to have other ideas. Yeah, go Shumit.
Yeah, Shumit?
I agree. And I just add one thing to it, that when we think of grain boundaries, we tend to just think of a grain boundary as a big channel where things just zip through. And one of the things that's turned out to be very important, and actually Katerina is the one who's done some work on it, is the solubility of elements in grain boundary. So there's really 2 things that are going on together: how fast things move in a grain boundary and how much of an element you can put in that grain boundary. And that depends on the material. So for example, if you have a lot of biotite, the argon may be behaving very differently from what it would do in an olivine rock or something. And this, grain boundary segregation factor is something that Katerina actually knows a lot more than I do.
So, yeah, taking up from Sumit, I think we cannot treat all the boundaries as equivalent and just say, okay, it's a grain boundary, so it will behave as a super fast diffusion pathway. As you may have seen in the last plot of measurements on grain boundary diffusion of different orientations, we could also already see that 2 different types of boundaries have 2 orders of magnitude difference in diffusivities. And that's just by changing the orientation. So one is more like a twin boundary and one was more like a random grain boundary, whatever that means in the context of your question. So it is, again, a local question. So what is this boundary doing with respect to what you are looking at? And yes, sometimes you may think of the grain boundary as a fluid. In the next case, the grain boundary will more behave as a single crystal. So yes, so not only do we need to know the crystals, but also their orientation and the structure of the boundary. So.
Yes. Any more comments on that?
Roy,
If not, I would.
also depends
Yeah.
on what else is in there. So yeah, I mean, orientation, it's a material, it depends on what else is sitting on the grain boundary. And yeah, I mean, there's a lot of different parameters that characterize a grain boundary, and depends on whether it's efficient or not, depending on that.
And I would argue as well, again, if, say, for example, we're looking at a mica next to, say, an amphibole, and the amphibole can also take up whatever the mica is spitting out, or vice versa, that's going to be very different behavior to if you've got something that's completely impermeable to whatever element that you're looking at. So where these atoms go, it depends on where the sink is for them. So I think, yeah, each grain is going to behave very differently, and so it very much depends on the question you're trying to ask of your rock.
I mean, if I may, that's exactly what I was trying to get to when I was talking about the embedding chemistry. You know, if you have an oxygen terminated surface, that behavior is going to be completely different from a magnesium terminated surface. And as Bruce pointed out, if that oxygen terminated surface has been water wet at some point, well, actually then you're probably dealing with a hydroxyl terminated surface, and its behavior with the mobility of a cation or an anion is going to be completely different.
I mean, I
Okay. Yeah, Schubert.
just one more thing that you know, I mean, this reminds me of times when we were looking at other things where people thought, oh, there are so many different things, and so in diffusion in crystal lattices, and physicists would tell you that oh, there, you know, each trace element can affect the diffusion rate, and how can you begin to do diffusion in natural systems which are so dirty, and so forth. And it's true, but then, you know, once we looked at some of those, we could figure out that there are some systematics, there are some trace elements, some things that really matter. For example, the trivalent cations in olivine, and not every other trace element. And it's the same sort of thing with grain boundaries, I think. I mean, now we are beginning to look at things on the grain boundary properties, and you're seeing all these things that can affect things. And it seems like you throw up your hand, so you'll never get ever to a real natural complex rock. But I think, you know, with a few of these studies, we'll find out some controlling factors, and then we will be able to quantify transporting grain boundaries in real rocks.
Okay, so
Tommy, did you see there was a question from John Wheeler?
yes, I did see this. So I would hand over to John. And I think there's another one from Chris. So let's first deal with John, and then we'll see.
Hi, yes. So look, I mean, this is a particular interest of mine. I guess my question is to all of you, but Sumit in particular. Sumit, you only hinted briefly at lattice strain as having an effect. But I think a back of the envelope calculation shows that when you've got lattice dimension mismatch in solid solutions, then if you try and fit those cells together, then you get really big stresses there. So, and I know that you've studied this sort of thing. So I wondered if you could somehow briefly tell us how that fits in the kind of list of things that we need to know more about. Do you think it's important, or where does it fit in relation to the other unknowns?
Oh, well, you know, you've opened me up to another talk now. So maybe just quickly as a background and as a note of thank you. So that's actually something I'm working on right now. So we have a paper in the review process, and because he was not anonymous, I think I can say that. So John did a very constructive, good review to that. So that's what he's pointing to. So it relates to some other discussions I've been having with other people. So I'll just pick up calcium in garnet, because that's what I was talking to Bruce about earlier. If you put in calcium into garnet, then the lattice parameter for grossular is much bigger than, let's say, certainly pyrope and even almandine or something. And like John says, you know, if you start putting in more and more calcium, and if you think of that, and I hope I'm right, John knows more about this, that if you think of it as you're putting in a grossular lattice into an almandine lattice, you're creating stress. And what ends up happening is you produce dislocations at some point. Some point you cross some threshold and you see some dislocations. And you've seen this in, not in garnets, but in perovskite systems, in experiments. And once you do that, then this business of grain boundary segregation again comes into play, because now, let's say this calcium has a choice between sitting on this dislocation or trying to make its own grossular lattice, and it starts partitioning between these dislocations, or which may then migrate and start forming new grain boundaries and so forth. So you can start forming segregated structures or not, depending on the magnitude of that. So yeah, the short answer, I guess, is that you put in things, you start creating stress, but then it just not keep going on in an unlimited manner. At some point, it starts making dislocations, and then things start beginning to partition between the regular lattice sites and the more defective lattice sites. So I don't know if that answers your question, John.
Well, it's very interesting. I think that there must be a stage before you reach the threshold for dislocation activity where it has some kind of chemical effect. And look, I don't know. I am driven by this back of the envelope calculation that if you know, everyone's seen a chemical zoning profile in garnet with calcium varying, and it means that the unit cell is varying, and that means that there's something that has to accommodate that geometric thing. And I just thought, if I can just add one thing, that actually, I realise, I'm sorry I won't be able to attend all of tomorrow, but I realise there's an igneous dimension to this conference, and one traditionally thinks of igneous rocks as not, or volcanic rocks at least, as not being.
Can I just add something to that, or a question, general question?
Of
Hi,
course,
Shumit.
Lucy.
Hi, John. Hi, everybody. Because this is, I think, a very interesting topic. What is the mechanical effect to diffusion? And of course, we mentioned garnet, and we have usually the approach in geology is that we assume that the components are of the same size, like FeMg calcium, which is not the case. There is a huge volumetric change or density change during that, and it must have an effect on lattice. Like lattice distortion and so on. And my worry is that, for instance, when these things are then used for like a time estimate, because then of course the question is like which reference frame for the diffusion calculation you use. And if it is the what is mostly used, I think that the constant volume reference frame, and then and we applied for like a time estimates, and the question is like how off can we be if actually we are not working with the volume constant material, if that makes sense what I just said. I mean, if you use it for trace element and you focus on diffusion of trace elements, I think that we can be safe there, plus minus. But if this is applied for major elements, major components, like for garnet, iron, magnesium, calcium, I think that there might be something which we can improve in future. I'm going to Claire's question. So it's not it's manpower, but also meaning in terms of like whether our physics, which you use, is appropriate one.
Yeah, and measuring again. So yeah, if you had a tool to actually observe it, that would be very good, because we all, you know, expect some effect, but we don't know if the effect's big or small, or, you know, really huge or negligible. And it'd be good to find a way to measure and put numbers on that.
Yeah, I think that also like a new design of like coming back or taking into account this or bearing in mind this mechanical effect, we can probably think about kind of new kind of experiments, because the current experiment, because my worry is that since the experiments are done at high temperatures, where the viscous relaxation is kind of like you don't see the effect properly. But then it's extrapolated to geological conditions where like around 800 degrees and below, we might have this mechanical effect there, which we don't see in the experiment. So I think that we can, so it would be nice to explore or to think about what kind of experiments, or if we can come out with some experiments where we could observe the mechanical effect as well.
Yeah, I'll define actually the challenge for all of you here, because this is something that's been on our minds and we don't have a solution. So all the young people here. So here's the challenge. So like Lucy said, you need to go down at low temperatures to really see a large effect. And when you go down to low temperature, the diffusion becomes slower. So you're looking at diffusion over a few hundred nanometers. And the challenge is to find a way where you have over these 100 nanometers or so, you can map out the strain distribution. So if there's a tool, if somebody has a way to do that, then we are very cool and in a lot of business.
EBSD. So in principle, you can
I
map
think Bruce
only.
wanted to.
Yeah, could I just mention about this question of what happens with volume changes when you start having things like diffusion of calcium in garnet and so on? I can immediately think of 3 situations where I have seen minerals that you can identify section have undergone diffusion because they have developed a very dark, clouded appearance. And I've never been able to finally resolve what it is that's causing it, but I suspect it's some sort of microporosity or fracturing. One case is in gabbros that are being incipiently eclogitized. So some of the Norwegian gabbros that have been in the eclogite facies but still have igneous textures, you have omphacitic pyroxenes pseudomorphing the original igneous pyroxene, and they look almost opaque in plain light. When I worked on diffusion in garnets in the 1970s, probe time was very expensive and difficult to get, but I could identify the garnets that had undergone diffusion because they were the areas that were almost opaque. And a third example, when you look at albertized plagioclase in altered metabasalts, again, albertization is very commonly accompanied by the crystal going almost opaque. Now, your gut feeling when you see mineral grains that look really cruddy and opaque is to study a different thin section. So I just urge you all to have a look at these messy looking grains, because they could be the start of some whole new problem.
Yeah, it's a very good point, Bruce. I mean, opaque.
And I didn't want to cut off Tinker here, who has the solution for us all in EBSD.
TM, of course. No, but for shorter profiles caused by local deformation, you can get a better understanding of that combining different methods in the TM. For example, precession electron diffraction, so you can see local orientation variation, similar to what you know from EBSD, but you can do that in the TEM and directly combine it with chemical mapping on the nanometer scale. So yes, for these challenging experiments, as you mentioned them, that might help a lot.
There's definitely a lot to be done, a lot of work to be done for future generations.